Hi, Year 12. I hope you're all good. Right, so this is the first of my pre-recorded lessons for this sort of lockdown period. So that means that you might be watching this and participating in this lesson in the morning, in the afternoon, in the evening. It's about you fitting it into your own schedule, okay? So the aim of this lesson, firstly, I'm going to review the homework task that I set you initially. So I'm going to go through the answers to that a step at a time. And then after that, we're going to move on to the first bit of the alkanes topic. Now, the first thing I'm going to mention about the homework is you've submitted all your answers online electronically. Now, for a number of these questions, there are actually sort of multiple options of correct answers. So do be reassured that if you put an answer in the on the online form and you thought it was correct, that I will actually be going through and doing a manual check, a manual mark of your work as well. I won't just be leaving it to the computer. And so in some of these questions, if I highlight here, oh, actually there's multiple options of an answer, then it might be that I might be amending your work a little bit, amending your marking a little bit. Okay, so I'm going to go through this first. If you found that you got most of this right, because it's a recorded lesson, you can, of course, skip through the bits that you're finding straightforward quick enough. Whereas if there's aspects of it which you find a bit more challenging, then you, of course, are able to, rewind and rewatch a bit more frequently. Okay, right. So the first bit of this homework was to name the molecules labeled A to T. So I'm going to go through that relatively swiftly to begin with, and then we'll move on to the other questions. Okay, so our first molecule, we've got 5 carbons in a row. 1, 2, 3, 4, 5. We've got a methyl group on 2 and a methyl group on 3. So this is going to be 2,3-dimethyl pentane. Okay, the next one, 5 carbons in a row. We've got a methyl group on 2 and 3 and 4. So it's 2,3,4-trimethyl pentane. And remember, commas between numbers, dashes between numbers and letters. And of course, you need to have your di and your tri in there as well. Okay, next one. A bit trickier this because we need to come up with the longest carbon chain first of all, and we've got a few options. We could have 1, 2, 3, 4, 5. We could have 1, 2, 3, 4, 5. So I'm not going to pick this one as the longest carbon chain because then we've got a branch which has got another branch coming off of it, and that becomes really complicated to name. So I'm going to call this our longest carbon chain here. 1, 2, 3, 4, 5, but I'm actually going to number it in reverse. 1, 2, 3, 4, 5. So we've got a methyl on 2 and we've got an ethyl on 3, but then we have to name them alphabetically. So it's 3-ethyl, 2-methyl pentane. Finally, for this one, it's a 6 carbon chain. So don't be fooled into thinking it's a 4 carbon chain with 4 branches. It's a 6 carbon chain, 1, 2, 3, 4, 5, 6. If that's carbon 2, that's carbon 3 and that's carbon 4, and it doesn't matter which direction you number it in, you end up with the same. We're dealing with 3,4-dimethylhexane there. Okay, right, moving on. Let me just fold that under and then we're nice and clear. Next one. So we've now got some alkenes to name. And the deal with alkenes is that an alkene is a high priority group, so it always has the lowest number possible. So here in this 5 carbon chain, 2, 3, 4, 5, this has to be carbon number 1 because it's where the alkene is. So that means we've got a methyl on 2, 3, and another methyl on 4. So it's going to be 2,4-dimethyl pent 1-ene. So 2,4-dimethyl pent -1-ene. Okay. Next, don't be fooled into thinking this is our longest carbon chain of 4, just because it's the bit at the bottom, kind of drawn in a straightish line. It doesn't automatically mean it's the longest carbon chain. Our longest carbon chain is 1, 2, 3, 4, 5. So our double bond starts on 2, and we've got a methyl group on 3. So 3-methyl pent 2-ene. Next, 1, 2, 3, 4, 5. But again, our alkene is our highest priority group, so we're going to number it in the reverse direction. So on carbon 2, that's where our double bond starts, but we've also got a methyl and another methyl on carbon 3. So it's 2,3-dimethyl pent 2-ene. And then finally for H, 1, 2, 3, 4, 5. 1, 2, 3 is my numbering. So double bond starts on 2. methyl on 2 and a methyl on 3. So this in fact has exactly the same name. This is also 2,3-dimethyl pent 2-ene. Okay. Next row. Again, fold that under again. So now we've got some haloalkanes. So we've got a 5-carbon chain. 1, 2, 3, 4, 5. We've got chlorines on carbon 2 and 2 and 4. So it's going to be 2,2,4 trichloropentane. Next one, 5-carbon chain again. I'm going to number it from the left-hand side. So we've got a chlorine on 2 and 3 and 3. So it's going to be 2,3,3 trichloropentane. Next, we've got a haloalkane, which also has a branch. So 5 carbons. It doesn't matter what direction we number it in. We're always going to end up with a bromine on 2 and 4, and we're always going to end up with a methyl group on 3. We just got to make sure that we include those groups alphabetically. So it's going to be 2,4-dibromo, 3-methyl pentane. Okay. And then last one from these, 1, 2, 3, 4, 5, 6 is my longest chain. If I number it 1, 2, 3, 4, I've got bromines on carbon 2 and 4, so it's 2,4-dibromohexane. Okay, next row. So like the remaining ones on this part of the task, you're starting off with structural formulae. Okay, now as a general rule, I would never try and come up with a name of a from a structural formula straight off. I would always try and draw the structural formula out first of all. So here I've got 2 methyls attached to a carbon with a hydrogen. So here's a carbon with a hydrogen, and I've got 2 methyls attached. One I'm going to put up, one I'm going to put to the side. I've got a carbon with a hydrogen and a CH3. So that's that bit and that bit. I've got a carbon with a hydrogen and a CH3. So carbon, hydrogen, CH3. And then I've got a CH2 followed by a CH3 at the end. So there's a bit of a trick with this one, or it's not a trick, it's just something to get used to. So we've got CH3, 2 at the beginning of the name. And normally when you see something in a bracket, you think, right, that's going to be a branch coming off the molecule. But actually in this situation, one of them is a branch coming off the molecule, but the other CH3 is actually the end of the chain. So we've now got 1, 2, 3, 4, 5, 6 carbons in a row. And then we've got methyls on carbons 2, 3, and 4. So this is JKLM is what I'm on at the moment. 2, 3, 4 trimethylhexane. 2, 3, 4 trimethylhexane. I'm just going to move my camera down a bit. Just I don't want it to be fuzzy if it doesn't need to be on the screen. Okay, molecule N. So again, I'm going to draw this out. I've got a CH3 on the end. I've got a CH2 next door to it. I've got a C with 2 CH3s. So a C with a CH3 up and a CH3 down. I've got a CH2. I've got a CH. And again, it says 2 lots of CH3. So I'm going to put one going down. But the other one isn't a branch. The other one is the end of the chain. So again, it's another example where I've got a 6-carbon chain. 1, 2, 3, 4, 5, 6. If I number it from this end, 1, 2, 3, 4, I've got a methyl on 2 and 4 and 4. So it is 2, 4, 4 trimethylhexane. Okay. Right. Oh, again, I'm not going to try and name it straight from the structural formula. Let's draw it out. I'm going to start off with this carbon here. Okay, now it says this carbon, it's got CH3 in brackets 3. So it looks like there's 3 methyl branches coming from it. Well, let's put one going up. Let's put one going down. And then the third methyl branch isn't a branch. The third methyl branch is the end of the molecule. Okay, so then we've got a CH2. So let's put that next door. We've got a CH with a CH3 branch. So C, H and a CH3 branch, CH2, CH3. So I'm in a situation again where I've got 1, 2, 3, 4, 5, 6 carbons. I've got methyls on 2 and 2 and 4. So it's 2, 2, 4. Oh, I've put 2, 4, 4. 2, 2, 4 trimethyl hexane. Okay, and then the final one on here. So again, I'm going to start off with this carbon. So there's that carbon. It says it's got a hydrogen attached, and then it's got 2 CH3s. CH3, and then the other CH3 again is the end of the chain. CH, and then C2H5. So next door, I've got a C with an H and a C2H5. So I've got an ethyl branch there. CH2, 2. So CH2, 2, and then a CH3 at the end. So 6 carbon chain, 1, 2, 3, 4, 5, 6. I've got a methyl on 2, I've got an ethyl on 3. These need to be alphabetical. So it's going to be, oh, I've written these the wrong way around. So let me get this right way around. O is, that's why I got confused, because, so that one is actually 2, 4, 4. So this one, apologies, I've done my answers, but I've written them the wrong way around. So molecule O is 2, 2, 4 trimethyl hexane, and molecule P is 3 ethyl 2 methyl hexane. Okay, let me just scooch that up there so you can see. Okay, final row of these then. Molecules Q, R, S, and T. So, same as last time, I would always draw these out. Now, you can't tell just by looking at them, but these are all alkenes, okay? If I draw it out, I've got a CH3 at the end here. I've got a C with an H, so that's that bit. I've got a C with a CH3 branch, so C with a CH3 branch. I've got a CH2, and I've got a CH3. So because these two carbons don't have enough bonds, that means there has to be a double bond in between them. So I'm dealing with 3-methyl pent-2-ene, okay, for Q. Molecule R. So I'm going to start off with this carbon. So this carbon has got a hydrogen. It's got CH3 2 attached to it. So that means a CH3 up, but the other one isn't a branch. The other one is the end of the chain. I've got a C with a CH3. So C with a CH3. Next door to it, I've got a C with an H. C with an H, and then a CH3 at the end. So again, another situation where we've got two carbons that don't have enough bonds. So that means there has to be a double bond between them. And then when we're naming it, we have to number, so the double bond is as low as possible. So this is going to be 3,4-dimethyl pent-2-ene. Okay, 2 to go. So we've got same little trick again. If I draw this CH out first, C with an H, it's got 2 methyl groups, so one's going to go up, but the other one isn't really a branch. The other one is just the end of the chain. Then I've got a C with a CH3. And then I've got a C with 2 lots of CH3. So let's put a CH3 up. Let's put a CH3 at the end here. And that means these two carbons don't have enough bonds, so there must be a double bond between them. So carbon 1, 2, 3, 4, 5. So I've got methyls on 2, 3, and 4. And then my double bond starts on 2. So this is going to be 2, 3, 4, trimethyl pent-2-ene. 2, 3, 4, trimethyl pent-2-ene there. Final one, I've got a CH3. So let's put that at the end, followed by a CH, followed by a CH, followed by a CH with 2 lots of CH3. So CH3 down, and then a CH3 to the side. So final situation where we've got 2 carbons without enough bonds. So that must be where our double bond is. carbon 1, 2, 3, 4, 5. So we're dealing with 4-methyl pent-2-ene, because again, the double bond is our high priority group that has to be as low as possible. Okay. Right, moving on then. The next question said, draw the skeletal and displayed formula of compounds U to X. Now, this wasn't on the Google form, the Microsoft form, because you can't really draw formulae like that very easily or upload your answers particularly easily. So I'm just going to whiz through these ones here. So 3-methyl hex-3-ene is what we're dealing with here. So as soon as I see the hex-3-ene bit, it makes me think, right, draw a 1, 2, 3, 4, 5, 6 carbon chain with the alkene on carbon 3, and that means the methyl has to go on carbon 2 there. So there's our skeletal, and there's our displayed. Make sure on your display you don't have too many hydrogens. The temptation is people end up attaching too many hydrogens onto the carbons which have got the double bonds. So just be careful about that. So no hydrogens, or not no hydrogens, just one hydrogen each on these 2 carbons. Make sure you don't have one going below, because you'll end up with carbons which have got 5 bonds attached to them. Okay, molecule V, 2-chloro-pent-2-ene. So again, I'd start off with the pent chain. 1, 2, 3, 4, 5. 2 is pent-2-ene, so let's have the double bond starting on carbon 2, and the chlorine on carbon 2 as well. And there's our displayed formula. Again, make sure the carbons on the double bond don't have extra hydrogens attached. Molecule W, 2,3-dibromo, 3-methyl pentane. So again, I would start off with the pent chain. 1, 2, 3, 4, 5. 2,3-dibromo, so that means I've got a bromine on 2 and a bromine on 3. And then 3-methyl, so I've got an extra methyl group on 3 as well. And as a display formula, that's what it would look like. It doesn't matter whether you have your bromines pointing up or down, doesn't matter whether your methyl's pointing up or down. The important bit is that they're attached to the right carbon. Okay, lastly, molecule X, 2,3-dibromo, 3-chloro-pentane. So we're dealing with pent again. So let's start off with a 5-carbon chain. 2,3-dibromo, so a bromine on 2, a bromine on 3. 3-chloro, so a chlorine on 3 as well. And then same equivalent for our display formula. Okay then, right, moving on. Question 3, give the molecular formulae for molecules A, E, and I. So let's just go back onto here a second. So molecule A, it's got 7 carbons in it. 1, 2, 3, 4, 5, 6, 7. So it has to start off with C7. You could count up all the hydrogens, but the fact is, this is an alkane. You can tell because there's no other substances attached to it. So it must obey the CnH2n plus 2 rule. So just by applying that, I know it must be C7H16. Molecule E, again, it's got various branches on it, but I've now got an alkene group on it. And alkenes obey the CnH2n rule. So if I count up that it's got 7 carbons, it must have 14 hydrogens. And then molecule I, 1, 2, 3, 4, 5 carbons. This probably is one that I would just count up, I imagine. 5 carbons. If I fill in all the gaps, that will have 3 hydrogens attached. That won't have any. That will have another 2. That will have 1, and that will have 3. So that gives me 9 hydrogens, and we can count up the 3 chlorines as well. Okay, question 4, empirical formulae for C, G, and K. Right, so for molecule C, again, it's a alkane because it's all single bonds, it's only carbons and hydrogens. So 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 carbons on there. If there's 8 carbons on there, and I know it obeys the CnH2n plus 2 rule, it must be C8H18. But that's my molecular formula. I can scale that down to C4H9 as my empirical. Okay. Molecule G is an alkene. It's got 7 carbons. So again, its molecular formula must be C7H14. That looks like it doesn't scale down, but it does because this scales down, because these are in a 1:2 ratio, this scales down to CH2. So that's our empirical formula for G. And then for K, if I go back to molecule K, I've got 1, 2, 3, 4, 5. I've got 6 carbons. Count up my hydrogens, I've got 12. Count up my bromines, I've got 2. And all of that can be divided by 2 to give us C3H6Br as our empirical. Okay. Question 5, give the structural formulae of D, H, and L. Right, so this is the main question where there are options of alternatives, okay, alternative answers available. So in molecule D, what's the best way to get this here? Let me shift that up there a second. So molecule D here. So the idea is you go along the carbon chain and state what's attached to it. So here we've got a CH3, followed by a CH2, followed by a CH and a methyl branch, so CH and a methyl branch, followed by a CH and a methyl branch, CH methyl branch, followed by a CH2 and a CH3 to finish things off. So that, I would imagine, is the answer you should be getting, okay? Molecule H, if I just look at molecule H, now the same thing applies. So if I go through in turn, I've got a CH3, then I've got a C with a methyl branch, so C with a methyl branch, then another C with a methyl branch. Notice that these 2 carbons don't have an extra hydrogen because they're the carbons of the double bonds. They don't have an extra hydrogen attached, followed by a CH2 and then a CH3. Now, I've started off at one end of the longest carbon chain and gone to the other end, but an equally acceptable answer would be doing the same in reverse. So if I started off with this one, I could say CH3, followed by CH2, followed by CH3, CH3, and then CH3. So on paper, it looks a bit different to the one that I've written above, but both of those are correct options. Finally, molecule L, so this one underneath it, same idea, CH3, CH with a Br, CH2, another CH with a Br, so that's there, followed by a CH2, followed by a CH3, okay? But just like with the previous one, I could do that all completely in reverse as well. So I could have CH3, CH2, CHBr, CH2, CHBr, CH3. So even though it looks different to the one above it, both of those refer to the same molecule. So either of those would be fine. Okay, question 6. So question 6 says, draw as many chain isomers of molecule A as you can and name them. Now, of course, you can't upload your different isomers onto the forms where I ask you to submit this work, but you could write the names on. So the following are the names I'm expecting. Molecule A was this. That was the structure you were given for molecule A. So the main thing we need to take from this is that this is a 7-carbon alkane. 1, 2, 3, 4, 5, 6, 7. So we've just got to play around with 7 carbons and see how many different ways we can arrange them. So option 1 is to just put 7 carbons in a straight chain. So that'll be pentane. We could have, and my recommendation would be to try and be as methodical as you can with this. That is the only 7 carbon chain option. So now let's go to the 6 chain option. So I've got 6 carbons in a row, 1, 2, 3, 4, 5, 6, with a methyl on carbon 2. So that's 2 methyl hexane. But I could have a 6-carbon chain with a methyl on 3. So that would be 3 methyl hexane. And that now is all the 6-carbon chain options. So let's look at 5 carbon chains. If I've got a 5-carbon chain, I need to have 2 branches on it. So I could have, there's my 5-carbon chain, 3, 4, 5. And I could have a methyl on 2 and another methyl on 2. So 2,2-dimethyl pentane. I could have a 5-carbon chain with a methyl on 2 and a methyl on 3. So that would be 2,3-dimethylpentane. Now that is actually molecule A. So that's not another isomer, that is molecule A, if we were being sort of picky about it. Next, we could have a 5-carbon chain with a methyl on 2 and a methyl on 4, so 2,4-dimethylpentane. I could have a 5-carbon chain, 1, 2, 3, 4, 5, with both methyl branches on carbon 3 in the middle, so 3,3-dimethylpentane. And actually, just as I'm going through this, I've just remembered there is actually another option, a 5-carbon chain, 1, 2, 3, 4, 5, with an ethyl on carbon 3. So that would be 3-ethyl pentane. That would also be correct. All right. Now, of course, just to go off on a bit of a tangent here, I couldn't have a 5-carbon chain with an ethyl on carbon 2, because as soon as you do that, you no longer have a 5-carbon chain. I know there's 5 carbons here, 1, 2, 3, 4, 5, but actually the longest carbon chain is 1, 2, 3, 4, 5, 6. So now we're actually dealing with 3-methylhexane, just drawn a bit differently. We already came up with that one at the beginning of the question. Okay, so then the last option is to see what can we do with 4 carbons in a row. 1, 2, 3. So I've got 4 carbons in a chain there. If I've got 4 carbons, I need to have 3 carbon branches. And my only option for that is to have 2 of them on one of the carbons in the middle and the other one on the other carbon. So the only option is 2,2,3-trimethylbutane. And again, I can't have any ethyl branches on this, because if I have an ethyl branch, it will no longer be a 4-carbon chain. It will turn it in, the longest carbon chain will become a 5-carbon chain. Okay. Finally then, question 7, same idea. So these are all, remember, these are all chain isomers that we've just done. So we're just changing the carbon skeleton. Question 7 was wanting different position isomers of molecule G. So here is molecule G. So the rule with position isomers is that the carbon skeleton has to stay the same. So in this question, we have to stick with 5 carbons in a row, a methyl branch on carbon 3, and a methyl branch on carbon 2. So I cannot move those. A position isomer just changes the position of the functional group, and here the functional group is the alkene. So I just need to play around with moving the alkene around. So I could have the alkene at the end, and if I did that, that becomes carbon 1, 2, 3, 4, 5. So it'll be 2,3-dimethylpent-1-ene. Keeping that same structure, I could move the double bond along one. And if that was the case, I'm still going to stick with the same numbering. So it's going to be 3,4-dimethylpent-2-ene. So I've got 2 so far. Next, I move the double bond on along one further to here. So this time I'm now going to start numbering in the opposite direction, because the double bond has to have the lowest number. So this is going to be 2,3-dimethylpent-2-ene. But again, remember, if the question asks you for isomers of, you can't include the structure again. So that actually is molecule G. So technically, even though that is a correct structure, it isn't an isomer of the molecule. It's just the exact same molecule again. Let's move the double bond along one further. So if that's the case, carbon 1, 2, 3, 4, 5. So it's going to be 2,3-dimethylpent-1-ene. So that's what we got there. Next, I could put the double bond as the branch. So rather than it being a methyl branch pointing up each time, let's have the double bond on the branch. And this is where one of our nomenclature rules is bent ever so slightly. So we kind of don't quite follow things as strictly as possible, because normally our golden rule is find the longest carbon chain. Well, we could do that, but the issue is the longest carbon chain doesn't have our alkene in it. So here, we're actually going to find the longest carbon chain that the alkene is part of. So we're going to go with carbon 1, 2, 3, 4. So if that's the case, on carbon 2, we've got an ethyl group, and carbon 3, we've got a methyl group. So it's going to be 2-ethyl, 3-methyl-but-1-ene, meth, eth, pro, but, double bond, starting on carbon 1. And then the final one, you might think, right, well, if I can have the double bond on that branch, let's put the double bond on this branch. So I could do that. But the thing is, you can't do that, not because it's not allowed, not because it's not a structure, but it's actually the same as one of the previous answers. It's actually the same as that one. Okay, imagine that there's free rotation about that bond. We could easily twist that up and it would end up with the double bond up here and the single bond pointing down. So it's actually the same molecule as that. Okay, so that's what we're looking for that final one. Okay, so that was a very quick whiz through of that homework. On the whole, done very well. But like I said, most people have a few little nitpick things to kind of work on. And that is always the same with nomenclature. It doesn't matter how good an organic chemist you are, there will always be organic molecules that crop up that make you think, oh, crikey, you know, this is quite a tricky one to name. So it's the sort of thing that you can never say you're fully mastered. You're always learning more and new complex ones. Okay, the remainder of this lesson then, I'm going to do a 10, 15 minute or so, a bit of like talk and explanation through the first bit of our alkanes booklet. And then you are going to have a go at some tasks independently. So you need your alkanes note booklet with you, and you need your alkanes question pack with you. Your question pack you can just put to the side for now, because I'm going to set you some work on that separately in a moment. But your note booklet is what you need in front of you at the moment. And all the stuff I'm going to go through in here should really just be a recap of some fundamentals that you'll have done back at GCSE. So I don't anticipate any of this is going to be brand new to you by any means. Okay, right. Firstly then, let's go through some definitions of alkanes. So you need to know the definition of a hydrocarbon. And the rule is it's a compound or a molecule containing carbon and hydrogen only. You absolutely must have that word only in there. Let me give you an example why. If I use the molecule glucose, which is C6H12O6, and I didn't have the word only there, I could say, oh, this is a hydrocarbon. It's a compound containing carbon and hydrogen, because it does. But the thing is, it's got some other elements as well. It's got oxygen, and that's not okay. So a hydrocarbon has to be hydrogen and carbon only. Okay? Saturated, what does the word saturated? It means single bonds only. Okay? And then finally, we're going to use those two key words in our definition of an alkane. So an alkane is a saturated hydrocarbon. It contains only carbon to carbon and carbon hydrogen single bonds. If it asks you this in an exam, you actually only need those first few words. Alkanes are saturated hydrocarbons. You wouldn't even need the rest of that sentence. Okay, you just keep it nice and simple to that bit. Okay, alkanes are saturated hydrocarbons. Okay, so a few definitions to make sure you're clear on. General formula. If anyone remembers anything about alkanes back at GCSE, they tend to remember the following, that it has a general formula. All alkanes follow the formula CnH2n plus 2, which means however many carbons there are, there's twice as many carbons plus 2 hydrogens. So let's go through some examples. Methane, the simplest alkane. Here, N is 1. We just don't write the 1 for a formula where there's only one of an element. But if N is 1, 2 lots of 1 plus 2 is 4. So this follows the rule. Ethane, C2H6. If N is 2, 2 lots of 2 plus 2 equals 6. So it follows the rule. So any molecule which follows that formula must be an alkane. Okay? Unbranched chains are always single bonds, okay? And the bond angle is usually 109.5. Hopefully you remember from your bonding topic that whenever you have an atom which forms 4 bonds, they form a tetrahedral shape, and the bond angle in a tetrahedral is always 109.5. So for alkanes, we always have this tetrahedral arrangement. So even though for, let's say, propane, we might draw it flat on a page like that, the reality is this is actually a 3-dimensional molecule, not a flat 2D molecule. So really, if I was going to be drawing that in 3 dimensions, it should look something, if I can fit it all in, like this. every carbon should have 2 straight bonds, then 1 dashed and 1 wedged bond. So H, 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 H. So all of those are going to have bond angles which are 109.5 because they all have tetrahedral bonding. Okay, we just use that structure, those 2-dimensional structures, quite often in organic chemistry, just to make it quicker and easier and simpler to draw these molecules. Okay, we already know that alkanes can be branched. So methylbutane is an isomer of pentane. All right, so rather than 5 carbons in a row, we've got 4 carbons with a branch methyl group, and you could represent that as a structural formula as well. Then there's a slight anomaly, which is cycloalkanes. I'll call them ring alkanes here, cycloalkanes. And these are a slight anomaly because they don't obey the CnH2n plus 2 rule. They just obey the CnH2n rule. So however many carbons there are in the ring, there are twice as many hydrogens, and that's because each of them bonds to 2 hydrogens each. Okay? Structural formula for cyclic molecules is a little bit different. So that would be the structural formula for cyclohexane as an example. Okay, nomenclature for the first 6 alkanes should be fairly basic to you now. Methane, ethane, propane, butane, pentane, hexane. To be honest, at A-level, I'd expect you to know a few more, though. If you had a molecule which was C7H16, after hex comes hept, heptane. After 7 comes 8, C8, H18. That's going to be octane. C9, H20 becomes nonane. And then after that, C10, H22 becomes decane. So yeah, I would still probably become familiar with those further ones after that. Right, and then the last bit I'm going to go through with you is just a little bit about their some of their physical properties, so things like melting point and boiling point. Okay, now first thing we need to know is the longer the carbon chain, the higher the boiling point. Okay, and I'm going to represent that with a few little scribbly diagrams. So here is some short alkane molecules, and here is much longer alkane molecules. And because alkanes have no delta pluses or delta minuses, they don't have any electronegative groups on there or anything like that. These are just relying entirely on van der Waals intermolecular forces. So because these are relatively small molecules, their van der Waals forces are going to be quite weak. There's not going to be very many of them because there's not very many points of contact. Whereas much longer groups, because they have a larger surface area, there's much more points of contact. So that means more or stronger van der Waals intermolecular forces. So all those van der Waals will need much more energy in order to break them. Okay, so how do we phrase that in an exam? If you're asked to explain why longer hydrocarbons have higher melting points, we'd say there's more electrons, or you could say longer or more mass. And that means stronger van der Waals forces. Now, we're also going to face a situation where we have molecules which have the same mass, but are branched in different ways. So let's say we have the following situation. Let's say we had C6H14. Lots of different ways of representing this molecule. We could have 1, 2, 3, 4, 5, 6 carbons in a row. We could have 1, 2, 3, 4, 5 carbons and a branch. I could have 1, 2, 3, 4 carbons and 2 branches. But these are still all the same formula. They're still isomers of one another. Okay, but even though they've got the same mass and the same number of atoms and the same number of electrons, these are going to have different boiling points. And the rule is the more branches, it results in lower melting points and boiling points. Okay, and that's because essentially you're taking kind of long, thin molecules and you're making them sort of shorter and fatter and rounder. Okay, so this is quite long and thin. This one's a little bit shorter and a little bit rounder. This is even shorter still and even rounder. And so this is going to have the smallest surface area compared to this one. Okay, I've gone off this bottom of the page there. Okay, so the more branching, the shorter they become, the more, yeah, like I said, they just become smaller in size, more clumpy, clump shaped rather than long and thin. And as a result, that means that they have a lower surface area. And so they're going to have fewer points of contact to form van der Waals forces with their neighbors. So if I show you here, we've got some straight chain meth but. So these are butane molecules, 4 carbons long. If we increase the branching, so let's make them 3 carbons long with a methyl branch, that reduces their surface area. So this will have a lower boiling point or lower melting point. Okay, reasoning for that, less surface contact, therefore weaker van der Waals forces. Okay, what I would like you to do at this stage. So this is, I'm kind of drawing to the end of the video bit of this lesson. In your new question packs, I would like you to have a go at tasks 1 and tasks 2. So let me quickly show you them very briefly. So task 1 is on the front inside cover. On the green cover, a few bits about what state different alkanes are going to be at room temperature, and it asks a bit about different formulae of them. And then task 2, the page over, you've got a few tasks about melting points and boiling points and what factors determine them. So you've just got 3 pages of kind of questions and tasks to complete from your alkanes. Okay, so I'm going to send this out with the instructions with this video, but once you've completed those 3 pages, I will need to upload them onto an online form for me so I can check that they have been done. So you need to either photo those 3 pages to upload, but I'm also just going to show you a bit of a trick on your phone. Now, this is iPhone specific. This is only because I have an iPhone, but I'll be honest, I'd imagine lots of you will have lots of different smartphones which have this capability. So let me just go back to this a second. So on your iPhone screen, if you go on Notes, and when you're on Notes and you're creating a new note, a new message, you can go on this button here, the one which is just a picture of your camera. And you can take photos, but it also says scan document. So if you go on scan document, you can actually take a photo of your work. So let's say I take a photo of my work there, but it turns it straight into a PDF, okay? And it will say keep scan, and you save that, and it turns it into a PDF, and it means you can upload it, you can save it on your phone, and it actually uses up a lot less data and a lot less storage, and it's easy to manage. Okay, so some of you might want to use that little trick if you are looking at uploading your work. Okay, so I'm going to leave you with that task to do. As ever, any questions, any worries, any concerns, anything you need a bit of help with, just get back in touch with me. At some point soon, you'll be getting some feedback via email on that nomenclature, isomerism, and formulae homework that you submitted previously. Okay, I'm going to do a bit of a mail merge to send out personalized feedback to each of you. Okay, right, as ever, keep working hard, stay safe, and I will see you in the real world at some point soon. Right, cheerio, bye now.